EX82. Let's talk about the filter phi-n module. Okay, so what we want to show today is the category of filter phi-n modules does not form abelian category. We will show that the co-image is an isomorphic to image for some particular example. Give a counterexample. So let's first basically quickly recall the definition of filter phi-n modules. So recall definition. A filtered phi-n module over K. So usually we work with just local fields, complete discrete evaluation fields with perfect residual field. Consists of, so we are going to define this filtered phi module. Firstly, consists of a phi-n module. Let's divide by D over K0. K0 is defined to be take the residue field of this local field K, and then take the weight ring and then invert P. We could define differently, saying that it is between QP and K. So K is an extension of QP, not necessarily finite extension of QP because we don't require the residue field to be finite. So between you could put a K0 here. It is the maximal unramified extension between K and QP, so which means the left part is totally ramified. Okay. And a filtration. On the K vector space defined by base change from K0 to K, such that for any integer filtration fit I of dk satisfy the following conditions. So there are sub key vector spaces of dk satisfy firstly field I plus 1 dk always containing field I of dk, so which means you have decreasing condition. So you have field 0, for example, so not necessarily starting from 0. I say -1, and then field 0 is contained there. Then field 1, right, etc. Second condition, we require the intersection of all the filtration is 0. This is very similar as separate when we talk about topology. Separated intersection of the power of the ideal is trivial, right? Separating. Third condition, the union of all the filtration. Is dk. We call it exhaustive. So maybe let me also recall here what is called a phi n module. Because the filter phi module, we said it was started with a phi n module. So phi n module over k0, defined similarly as above. Is a k0 vector space D. Let's denote by D and then equipped with, of course, two operators. So two maps phi n. First map phi, second map n, both defined from D to itself with the following properties. First requires phi is injective and semi-linear. We'll discuss what is a semi-linear map with respect to the absolute Frobenius. Sigma on K0. So this means that over the coefficient K0 there was already absolute Frobenius there, and semi-linear means this phi acting on the coefficient elements from K0 is equal to this absolute Frobenius acting on that element. Secondly, this operator n is a K0 linear map, not like phi semi-linear. This n is linear, and we call it monodromy map. Thirdly, this phi doesn't, phi n doesn't commute. The relation is given as follows. Okay, so we have recalled what is phi n module and what is filtered phi n module. So we will see that those categories can be used to classify color representation, certain color representation, crystalline representation, etc. Okay, so what is the exercise for today? Let me first describe the morphisms for filtered phi n module. As you could imagine, this is basically linear transformations between, basically isomorphisms of K0 modules. So morphisms of K0 vector space of linear transformations compatible with the two structure Frobenius and monodromy. So a morphism. So this is not part of the, let me remark. The morphism for filtered phi mod is as follows. Morphism F from D1 to D2 of filtered phi modules is a morphism of phi modules such that the induced K linear map base change to K satisfies f of k fill I d1 base change to k contained in fill I d2 base change to k for any I integer. So we base change to k because by the definition the filtrations are defined when after you base change to k. Okay, so here we use morphismal Fine module, so let's recall that also. So I should first recall this, of course, then define that. So there is reverse, sorry. So morphism between two phi n modules is just a k0 linear map commuting with, so if we're talking about finite dimension, this is just a linear transformation between vector spaces commuting with the two structure phi and n. Equivalently, if d1, d2 are two such phi modules, then we require f phi 1 equals phi 2 f n1 equals n2 f. That's all about this morphism. Third remark, so I'm going to give a notation. The object we want to talk about today, the filtered phi n modules form a category which we denote as mfk for Venice, and the full subcategory of objects for which n equals 0 is denoted mfk phi. Okay, so today's exercise is, so let me put remark. I'm not ask you to prove this, but these two categories are both additive. Additive category. So exercise today is to show they are not abelian category, which means give me a counterexample that some extra abelian category is not satisfied. Okay, solution, a counterexample. This counterexample comes from Stack project on the internet. Very easy example. The idea is that I construct a isomorphism. The underlying vectors and the underlying module are the same, but their filtration are different. But basically the coimage and the image of our example would not be isomorphism, and so not abelian. And which means that the filtration gives some complexity. So let D1, D2, let's take 2. And it's the same counterexample works for both. MFK phi n or MFK phi. So MFK should means module filtered, module filtered modules with phi n structure. So let me take an example here. With D1 equals D2 equals K0 equals K as K vector space. And I'm going to describe, because you have to describe the filtrations to describe objects here. So for D1, I'm going to describe its filtration for I less than 0 with D1, otherwise it's 0. So basically this is D1. So this is, let's say, I equals -1, I equals 0, I equals 1, I equals 2. This is D1, and then 0, 0, 0, right? While for D2, let's say filter mode D2, I'm going to define very similarly, but I less equal than 0. So this would look like D2, D2, 0, 0. Okay, so this is equality, and then this is included. And now we consider the map identity on the underlying vector space, but not on the filtration, because the filtration are different. Underlying vector spaces. So we set small f identity of K, and which means we set f to be this just constructed map, and we observe f has trivial kernel, trivial co-kernel. So because both are just 0 with 0 filtration, right? It's just totally trivial. And this is compatible with filtration because f fill ID1 is always containing fill ID2. As you could also read from the picture here, because it's just identity map. But here is the point. F is not an isomorphism of filtered finite modules. Also, so which means D1, D2, that basically they are they're not isomorphism as filtered fine modules because they have different filtration, right? But they have the trivial, there exists a map between them which has trivial kernel and co-kernel. If it's abelian category, then trivial kernel and co-kernel implies the isomorphism, but indeed they're not. Also, we could also argue that it's not abelian category by the following observation, that is compare the coimage and the image. So the coimage of F is, as a filtered fine module, is the one itself. Sorry, this is let me think. Kernel. So coimage is definition. It's defined to be f of d1. So maybe let me add a remark here. So remark, let me recall in this category of filter fine module, in the category of filter vector spaces even. For a map F from D1 to D2, in the most general category, let's see, fit K, let me quickly explain this. Fit K is defined as the category of finite dimensional K vector space. Equipped with a decreasing filtration indexed YZ, which is exhaustive and separated. So very similar as before, as you could guess. What are the conditions? Let me describe. So firstly, fill I of D on sub vector spaces of D, and then there is decreasing and then fill I of D equals 0 for I bigger, big enough. In particular, this tells you the intersection will be 0, so separated. and the union would be dn, so exhaustive, because we require this to be d when I is smaller enough. Okay, so as you could guess, what has morphism. So let me go back here. So for a map f from d1 to d2 in field of k, there are some following here. There are notions of image, let's say there are two notions of image with same underlying space, but distinct. Distinct means not isomorphism in this category. So firstly, we define the image of f to be f of d1 with, so this is containing d2 with the subspace filtration from d2 and we define the co-image of f to be still fd1, but with the quotient filtration from d2. Equivalently, co-image of f is defined to be, so of course, because the category of key modules or R modules is abelian category, so just the underlying set of the co-image is always underlying module, the co-image is always isomorphic to the image. But the filtration is defined differently, so here gives a different filtered space structure with the quotient filtration so we'll keep it f from d1 to d2. And the image of f equals the kernel of d2 to the co-kernel of f with the subspace filtration there is, remark 2, there is canonical map coimage of f with the image of f in this category filtered vector spaces. That is a linear bijection, but not in general an isomorphism in this category field I of k. Sorry, what did I write? But doesn't matter because as a module T1 T2 are the same. Okay. Here we are just describing this module and then the filtration. It's better to put it D2 because we're using the filtration on D2, but then take the quotient. Here we're using the filtration on D2. Two different filtration. So let's coming back to our counterexample here. We claim that the problem is the coimage of f as a filter fine module is D1, while image of f as filter fine module is D2, and so they're not isomorphism. Hence also imply this is not abelian category. So the image of f would use the filtration as the same filtration as D2, and so altogether it is just D2. While the coimage of f is used, if you remember, D1 quotient by the kernel, which is 0. Basically, it's using D1 quotient by kernel is the same filtration as D1. Let me think. Yeah. I will write FD1. Okay. I will write FD1. That's the counterexample.